Hello, my name is Cormac Molloy. This video demonstrates my Assignment 3 submission for the IoT module. In this project, I've designed and implemented a smart wearable rehabilitation system that collects live step count data from a wearable device, then ingests it into a MariaDB database using Node.js and Bluetooth Low Energy, and visualizes the data in Grafana. I'll now demonstrate the system end-to-end, including the device, lab data ingestion, database structure, dashboard visualization, and GDPR considerations. Here is the Fitband rehabilitation device. I will begin by running the MicroPython firmware on the wearable device using Tony. This code configures the BMI 160 accelerometer over I2C, uses hardware interrupts to detect steps, and maintains a cumulative step counter. This device exposes the data over BLE using a custom GAT service, broadcasting step count, activity level, and goal status. Now run the code. You hear the sound up, and it goes into blue base mode. And steps in this period 0, and once I start implementing steps, green means good activity. As you can see, it is implementing my steps. Next, I will run the Node.js ingestion service. This script acts as a BLE central device, connects to the Fitband, subscribes to step notifications, calculates steps per 5-second window, determines the activity level, and inserts the data into a MariaDB database. So, enter, connecting, scanning for the Fitband, connected to the Fitband, listening for step notifications. I will now start adding steps. That's for over activity levels, as I did too many steps. So total 11 in the window. I did 7. Now I did 0. Going to add more steps in the window, and you can see that I'm increasing my activity level, and the device is corresponding. As you can see, I reached the step goal. Here we can see the database updating in real time. Each row represents a 5-second activity window, including the cumulative step count, steps in that window, and inferred activity level. Now run it again, as I've done no steps here recently. And as you can see in this window, 0 with the total 21, and I will do some more steps. Run the code again, and as you can see, more steps in this window. I'll now show the tables. The database consists of 5 relational tables designed to separate concerns and support GDPR compliance. The patients table stores pseudonymized patient information. Each patient is identified by an internal ID and a pseudonym, with optional rehabilitation stage and clinical notes. No directly identifiable personal data is stored, which supports privacy by design. The rehab devices table represents physical wearable devices. Each device includes a serial number, firmware version, step goal, and an optional link to a patient. This allows devices to be reassigned without duplicating patient data. The parameter table defines measurable system parameters such as cumulative step count. This abstraction allows the system to be extended to additional sensors without changing the database schema. This junction table links parameters to devices, allowing per device configuration and scalability. The step measurements table stores all time series IoT data. Each row includes a timestamp, cumulative step count, steps in the last window, activity level, and whether the step goal has been reached. I will now demonstrate the Grafana dashboard connected directly to the MariaDB database. It is called the Fitband Rehabilitation Dashboard, with a gauge called Current Total Step Count and a time series of Fitband stroke rehabilitation step count over time. As you can see here, the gauge is for the entire step count goal, which I set to 20. In this demonstration, I reached 26 steps. So as you can see, it has gone all the way up and reached the goal of 26. Red zones was in low activity levels, orange is for medium activity levels, and green is for a great amount of activity levels, and you have completed your step goal. As new data is inserted into the database, the dashboard updates automatically without reconfiguration. The time series graph of the step count shows the time here and the amount of steps done. So as you can see, initially we did a total of 4 steps, and it is slowly increasing here during the time period of which those steps occurred. To summarize, the system consists of a wearable device collecting step data using an accelerometer, BLE communication to a Node.js gateway, real-time ingestion into a relational MariaDB database, and live visualization using Grafana. This architecture demonstrates a complete IoT data pipeline suitable for rehabilitation monitoring. From a GDPR perspective, this system is designed with data minimization and privacy by design. Patients are identified using pseudonyms rather than names. Personal data is stored separately from sensor measurements. Device data can be anonymized or deleted independently of patient records. And in a production system, additional safeguards such as access control, encryption at rest, and data retention policies would be implemented. This concludes the demonstration of my Assignment 3 IoT system. Thank you very much for watching. I will briefly explain the SQL series used to extract data from the database. These queries are required to generate the time series graph and the gauge visualization. Query 1, the gauge panel. This query retrieves the current cumulative step count for the device. Because the step count total increases monotonically, the maximum value represents the most recent total. This query is used by Grafana to drive the gauge panel, which shows progress towards the rehabilitation step goal. Query 2, the time series graph, returns timestamped step count data. The measured _@ column is aliased as time, which is required by Grafana for time series visualizations. This query is used for the line graph showing how the step count increases over time. This query 3, activity context, which is just supporting analysis. It provides additional context by showing steps taken within each time window and the inferred activity level. Although this data is not directly visualized in this dashboard, it demonstrates how the database supports richer analytics and future visualization options. Together, these queries demonstrate how structured relational data can be extracted using SQL to support the real-time and historical IoT visualization. Before concluding, I want to briefly highlight that I have added additional Grafana visualization features beyond the required graph and gauge. These will include to provide greater analytical depth, particularly around patient activity patterns, and to demonstrate how the same data set can be interpreted in multiple clinical, meaningful ways. This panel is a state timeline visualization that represents the patient's activity level over time, derived from activity level field in the step measurements table. Each colored block represents a categorical state: inactive, moderate, and intense, calculated for every 5-second window. Unlike a traditional time series graph, a state timeline is particularly effective for categorical data where the value itself is a state rather than a continuous number. In rehabilitation context, this allows clinicians to quickly identify periods of inactivity, bursts of movement, and changes in patient engagement without needing to interpret raw numerical values. This visualization is driven directly by the following query, which selects the timestamp, steps per window, and the derived activity level for the device. This second additional panel is a bar chart showing the number of steps detected in each 5-second window. Each bar represents a discrete sampling interval, allowing us to clearly see bursts of activity versus periods of inactivity. While the time series graph shows cumulative progress and the state timeline shows categorical behavior, this bar chart focuses specifically on movement intensity per window. This is particularly useful for validating the activity classification logic, as higher bars directly correspond to moderate or intense activity states. From a rehabilitation perspective, this makes it easier to assess whether a patient is performing short, meaningful movements, like you can see here, or which is more often important than total step count alone during early or post-stroke recovery stages. These additional panels demonstrate how Grafana can be used not just for monitoring totals, but for behavioral analysis, clinical interpretation, and data validation. By combining numerical, categorical, and temporal visualizations, the dashboard supports both technical monitoring and clinical decision-making. Together with the gauge and time series graph, these panels fulfill the requirement for the 2 core visualizations, while also demonstrating additional Grafana functionality. This approach reflects real-world IoT healthcare dashboards where multiple visual perspectives are required to fully understand patient activity and system behavior. Thank you very much for listening.